going to condense it. I generally prefer to write more in terms of mole fraction if it is there, because then the component balance is very simple to do. You can of course write the number of moles also, but then you will have to divide through by 100 or whatever is your basis. Like suppose you start with 100 moles per hour, then you have to divide everything by 100. So I prefer to put it in as a mole fraction. So to identify the total volumetric flow rate or mass flow rate of that stream. Temperature, pressure, I don't particularly like to put. We are not doing a proper piping and instrumentation diagram. For a balance, it doesn't matter what the conditions are, right? We are not interested in the process conditions or optimizing that process. We have been given the streams and we are trying to put all of that information. So this is true for all the problems that we will be doing in this month, right? Then the next is what I just mentioned to you in words. Look at the item in bold. You have to give those symbols. He has chosen, for instance, so much solution is flowing per minute, so that is m dot. Small x is, now it's very not clear what he means by small x. I mean, generally I reserve small x for a mass or mole fraction. But here, when you say pounds of nitrogen per pound of what? Is it per pound of all the gases that are there? If suppose it is nitrogen plus oxygen, or is it per pound of oxygen? Is it per pound of air? What is it? So that is a little bit ambiguous, but generally I reserve small x for a fraction, whether mass or mole. And here he has said n is for total number of moles. If you have a batch process, we want not a flow rate as we said, but total number of moles. So he gives you two examples. You can just see that, because here in the first one, the n dot, the molar flow rate is not given to you. So that is a variable. Again, I don't like to put the dot all the time because that's an extra symbol. But okay, everybody follows their own notation. So for me, that is Q, right? Volumetric flow rate or molar flow rate in moles per hour, etc. Right? Now, in the second case, he says flow rate is given. So he writes that it's not an unknown. So 400 you will put it, and compositions are not known. Again, his small y is a mole fraction here. So when he uses, in this case, what he means is moles of oxygen per mole of total gas. Okay. Similarly, 1 minus y, there are only two components. He's assuming there are only two components, nitrogen and oxygen. So 1 minus y will be the moles of nitrogen per mole of air. So this you have to label. So this way you will have in one diagram, you have distilled all the information from that problem, interpreted it and put it on the diagram. You have put it on the diagram. You have been able to identify what are the known facts about this process. What is the information that is known? You have given symbols and you have written those variables in terms of these symbols. So you know what the unknowns are. So you will know how many unknowns have to be solved. And now you will see how to write the algebraic equations which relate these variables, which I think generally our students are pretty good at doing that, right? But obviously we want to do, if it's a 1 hour exam, we don't want to unnecessarily solve for all, write 6 variables and 6 equations and then simultaneously solve them is a nuisance. So we must see which one we should start from. Generally we ought to start from the minimum number of variables, or we should first try that balance which gives us one of those variables directly without putting them in an equation which involves solving several variables simultaneously. So that principle would be very good if one can if you can follow that all the time. So let us try a proper example, and then after we do 1 or 2 such examples, we can again come back to these rules and see how to improve them. Okay, these are just overall rules, and many times we have to scale up things, and I haven't discussed that yet. We haven't come to that yet. So that introduces other complexities. So we may have to assign, we may have to provide these rules a little more detail, but that is later. Let us try based on this some examples. Right. So again, it's a continuous process. You are given, there is air, and there is, I mean, any humidification or dehumidification process involves air and water system, right? But here, in addition to flowing air, he has a third stream, which he says is pure oxygen. That is what is item C. And the flow rate of that pure oxygen is also given, but in terms of the flow rate of the dry air, right? So in other words, what he has done is he has given one variable in terms of the other variable in B. So we don't need to have additional variable C, but we can express it in terms of air, dry air. Now what he says is, like we do in any air conditioning operation, he looks at the output air, analyzes its contents, and tells, oh, इसमें इतना मोल % water है. So in other words, it gives you a criterion for the process. So here he says it is this much. Now he's asking us, what are the variables that are unknown and how we will label it, how we will then calculate it. So first is to draw the diagram, identify the known streams, identify the unknown variables, then put all that information in the diagram on the streams, and then we can see what overall balance and component balances will give us the unknowns. So please try this. As you will try this, a new problem also surfaces which we did not have in our yesterday's, so we have to also worry about that. So what is the difference in this question and the earlier question? Again, there are some similarities, some additional aspects. Similarity, still we have a single process unit. Number of streams have now increased. It's no more just benzene, toluene. There are 3 streams now. Input streams, I mean 3 input streams. But now there is also, it's a humidification problem, right? So water is also there and gas is also there. So you must separate out those streams and write those variables. Now, what are you going to take to solve it? You can start, you can say 100 moles of mixture B or B plus C. But if you are given a particular flow rate, like in A, that can be a valid basis on which the other unknown streams can be calculated. Did you get me? since he has given us what is A, he has given us an actual value. In this problem, it will not matter. You could do it whichever way you want. But if you have many more complexities, which we will see as next week onwards, then sometimes it may be beneficial to take as the basis the flow rate that is given to us. That is liquid water 20 centimeter cube per minute. That becomes a basis. On its basis you can calculate all the other streams, what values, magnitudes or flow rates they have, what compositions they have. Okay, so now you can try it out. I suggest just distill all of it into a diagram. If you can draw the diagram right, then you will solve it right. I am sure our students are very good at calculating some things, but you have to interpret it. If a diagram पे आपने ठीक नहीं draw किया या कोई, if you miss out a stream, that's it, right? The entire thing will go. By the way, in IIT Kanpur Chemical, I had, we all had to choose certain things. So I sort of had uh, the entire balance for a urea plant. That was one of my real big sheets, and the other was humidification and dehumidification operation, much more complex than what is given here. I mean, in auditorium design and all, we have to maintain not just temperatures but also humidity. So these were the two types of things on which I've done a lot of work, though it's nothing to do with my research. But anyway, here this is a very simple one compared to stuff that we normally have to do. But let us start with it. So in other words, you have to first draw the flow chart. So how many streams are entering? What is the number of flow streams that are entering the chamber? I just asked for the number, very simple question. right? 3 streams are entering, correct? Okay. How many streams are exiting? In this case, just one. So problem is very simple. Normally you can add complexity to that also, but here only one stream of the output gas is exiting the chamber, the humidification chamber, right? It's only one stream exiting. So now label those 3 streams that are going in and the one stream that is going out, just like you have done earlier. But now number of streams are more than earlier. Unit is still the same, one single dehumidification chamber, the number of streams have increased. So first label those, just draw those streams. How many moles per minute or whatever of the airflow is there? Is that known? No, right?
Unknown.
It's not known. So give it a variable like capital Q or whatever. Now 1/5 of that is also given to you as molar flow rate. So that stream also you can now label in terms of the volumetric flow rate symbol that you chose for stream B. Compositions of those streams are known. Stream C is only oxygen, so single component. What about stream B? It is a mixture of 2 components, so label the fractions, give a symbol for that, X or whatever. Normally for gas I use Y, for liquid I use X, but you can do whatever you want. So identify their molar fractions by a symbol. Because if Q volumetric flow rate of air is flowing in, 1/5 of Q is also flowing in a separate stream, which is a single component pure oxygen stream. So its molar flow rate can be 1/5 of the molar flow rate of the stream in B. What else is entering?
Water.
Very good. So give a symbol to that. Do you know the flow rate of the water?
Yes, sir.
Very good. It's given to you. The volumetric flow rate is given to you in centimeter cube per minute. But please convert everything to the same unit. Like this is a volumetric flow rate, but in that B and C you were looking at molar rates. So you should convert one to the other. You know the molecular weight, so you can convert one to the other. I mean, obviously, you have to keep all the flow rates in the same units, right? If something is a volumetric flow rate, another is a mass flow rate, something else is molar flow rate, then so it will be a lot of trouble. And if we fail to, because the answers are also important, and we do the calculation and then we don't differentiate between these 3 types of flow rates of volumetric mass flow and molar flow rate, then everything will go haywire, no? So please convert one to the other, say to molar and basis and to molar flow rates, and so according to you, how much is the volumetric flow rate corresponding to in molar terms? And give this stream a symbol. What symbol? L for liquid or water, W for water, whatever you want. See, the problem for us is C is given molar flow rate, no? So that we said is Q or whatever, or capital Q, and A we said is capital W. But the problem is that is not molar. So convert it. Tell me how much value you get. Okay, my question was all right. All I'm asking is,
So will it be 10 by 9 moles per minute?
10 by 9.
Okay, you know the density of water?
1 gram per
1
cc.
gram per ml.
So yeah, so basically you can convert the volumetric rate to a molar flow rate of water. So that becomes 10 by 9 moles of water per minute. Per minute. उसको label करिए. Because another thing you have to worry, sometimes units are in something is per second, minute, per hour. So that's another thing you have to watch out. Okay. Make sure everything is in terms of minute or hour or whatever. Keep it all the same. नहीं तो गए काम से. Especially in larger problems, if you miss that, you're all it's a simple oversight, but everything will go. You have to be careful. So it corresponds to 10 by 9 moles of H2O per minute. Very good. You know the composition of the stream A and B, right? So please label that. Because you were sending in capital Q moles per minute of air, right? But uska composition to pata hai hame. It's given in B. That in item of information in B is you have to put that in the on the diagram. We know the mole fraction. So it says 21 mole per, so fraction is 0.21 and 0.79 of nitrogen, that we know. So you are going to put that also on the diagram. Now what about stream A? Sorry, stream C. What flow rate does it have?
2/5.
1/5 of the flow rate of whatever you call stream B. So 1/5 times whatever you labeled stream B, whatever symbol you gave to that. M dot or Q, mole dot or Q or whatever you have called it. Correct? 1/5 of capital Q is the moles per minute of the pure oxygen. So you have found out that there is 10/9 moles per minute of liquid water coming in, that there is capital Q of air coming in whose composition is known, and you have also found there is the pure oxygen which is 1/5 of capital Q. These are all the input streams. Now, question for you. What does the output stream contain? What all is present? What is the analysis of the output stream? Input to you have identified now. Nice, very good. What about the output stream? What all does it contain? Again, you have to identify what all it contains correctly, right? Otherwise, वो पूरा गड़बड़ हो जाएगा again.
So oxygen, nitrogen, and water vapor.
Water, very good. Do you know at what rate that output stream is flowing? No, you don't know. That is a variable. So please give a variable to that. What do you want to call the output stream? You call
N dash something.
right. N dash. Or generally, I don't like to put dashes and dots because the chances of error are very much high with these dashes, double dashes, subscripts. So give it another symbol, preferably. O for output or F for flow rate of the output, whatever. Capital F. Now, within this is just the overall flow rate of that stream. उसकी composition के बारे में क्या पता है आपको? Please identify that information.
So 1.5 mole percent is water vapor.
Okay. What about the oxygen and the nitrogen, the other two components which you have correctly identified? What about them?
So we'll have to balance to find them. Okay.
Yeah, but you have to first label. I mean, उनको तो variable है, वो भी नहीं पता ना कितना oxygen fraction है, कितना nitrogen है, ये भी तो नहीं. Ratio तुम्हें पता हो सकता है ने, but तुम्हें वो तो नहीं पता ना. I mean, you have to. I mean, those are also unknown, no?
So we can take water as 0.015 and
Very good. So
oxygen is
mole fraction of water is 0.015. So how much is left for the other two?
0.985.
Okay. So some part of this is nitrogen, some part of this is oxygen. So please include that information in the output now. How many moles per minute? Or rather, how much, what is the mole fraction of oxygen per mole of total mixture, gas mixture, which as you have said has three components. इसमें की 0.015 तो water है तो उसको निकाल दिया आपने. if X is the fraction of whatever you want, say oxygen, then how much of nitrogen is there?
0.985
minus X.
0.985 minus X. Wonderful. So please label all of those information on the output. Have we missed out anything? You now have 3 input streams, you have 1 output stream. You know how many moles per minute of water is coming in. You know what is the fraction of the oxygen and nitrogen in the dry air that is flowing in. You know the volumetric flow rate of the pure oxygen as a function of the molar flow rate of the dry gas. And you know the composition, how much water was there in the total output stream. So you could have, for the unknown variable of that stream, capital F or capital O, whatever you called it, what fraction is nitrogen and what is oxygen. कितने वेरिएबल्स निकल रहे हैं आपके? How many variables unknowns are there now? Very good.
3.
So we need 3 equations to get these. Where will they come from? इस पर सोचिए. So this is the way it is put. 1/5 he has put as 0.2, which is fine. Composition mole fraction of N1 dot he has put, okay, 20 centimeter cube per minute. You already converted it to mole per minute, which so you can put 10 by 9. But N2 dot is actually known, no? N2 dot is just what you have just now told. So I would say you can just label that as 10 by 9 in moles per H2O per minute. I mean, why add an additional variable unnecessarily? You already know that. You converted, I mean, it was given to you, right? So please put that as 10 by 9. Now let's go to the output. He has called it N3 dot. I don't like this dots and subscripts, but okay. 0.015, 0.985. Yeah, looks okay. So you have to now find N1 dot in terms of this labeling. You have to find N1 dot, N3 dot, and Y. Three variables, like you correctly said. Now see where you are going to get those equations from. One overall balance we can do, that will definitely total balance of moles, that moles per minute, that has to work out. So that will give us one equation. What component balance can you do? You have oxygen, you have nitrogen, you have water. Obviously all are not independent. So which one should we do? Normally we do it at the end. So you can choose actually any 2 of those 3. So you have 3 independent equations then, the overall balance and any 2 of the component balances. You will put them all together. Ideally you should not solve them simultaneously but sequentially. So see what is the best way you should solve them so that you get the sequence. Obviously if you go try the nitrogen balance first, there will be all unknowns only. Or oxygen balance, if you put, it will be unknowns. So you have to use 2 component balance and overall balance in the right order and sort it out and solve it. I wouldn't use the oxygen balance first, nor would I worry about the nitrogen balance first, because it will just give me all the 3 unknowns in the same equation. You can write the equations in any order. I have no problem, but I wouldn't solve them in that way. So which one should you start with? Or what is one best way to start with? That is fairly easy because here you have only three variables, three unknowns. As the number of unknowns becomes larger, it's not trivial. But anyway, we have not reached there. So which balance would you do first? Definitely water. Water, definitely. Because you see, because he gives you that extra information, no 0.015 fraction is given as water. So that will identify you the stream itself. You know how much water there is coming in. There is nothing, no water is coming in from stream 1 and 2 on the left hand side. There's only water coming in from the bottom stream. And that you already told is 1.11 or whatever, 10 by 9 moles per minute. And you know the composition of the exit stream. So water balance will directly give me N3 dot straight. Because N3 dot times its mole fraction 0.015 must be the amount of water in moles per minute that is coming in through the bottom stream, which is 10 by 9. So please put this in the form of equation and get N3 dot. It's the only variable because W or N2 dot you have already told is 10 by 9. So that directly gives me N3 dot. Now do an overall balance. Total material balance. You know how much total streams are flowing in, उनके volumetric flow rates या molar flow rates पता है. You know capital W or what is called N2 dot here, and you know N3 dot. So now find N1 dot. Then once you can find that from the overall balance, then small y is the only unknown. So you can do a oxygen or a nitrogen balance and get that remaining unknown. Okay, we will. You can try it out, and Monday we can just finalize this thing, and then we want to go to a little more difficult questions where there are more than one unit. Okay, so what all we have done is we have started with the same type of single unit stuff like yesterday, but now we have added some more information in terms of the number of streams that is coming in, going out. And in this dehumidification operation, we had three components, so a little bit more interesting than the simple distillation benzene toluene system that we considered. And you found a nice way to draw the diagram, write the arrows, identify the input streams, write the information of the total volumetric or molar flow rates as well as the composition of those streams on the diagram itself. Then identified what the unknowns were. Then you saw how many there were. Then you saw how you are going to get those equations from. And then you saw what is the best way in which to solve those algebraic equations, in what order you should take. So this is the principle that we use repeatedly. Okay, we will go to some more realistic problems next class. Okay. Good luck, yeah.
Sir, on Microsoft Team, the recorded video will not 21 days. So you can upload it over Imparter, sir.
I did not hear you.
Sir, on Microsoft Team, the recorded video will not longer than 21 days.
Oh,
so
okay.
It can uploaded it over Imparters.
Okay, I will see how to do it. I haven't done it before, but I mean, it has come just naturally. So I don't know how useful it will be, but okay, we will do it. Okay,
Yeah,
thanks.
sir, is there any notes apart from slide PPT? Because some of us.
This is all common sense, no? This is all common sense. What else are we doing? We are just doing balance. In this case, we are just doing input equal to output. इसमें हम क्या notes दोगे? So, somewhat, starting with something very trivial, at least something with unsteady state I can understand. इसमें तो कुछ है नहीं. So just input is equal to output. What else can be told?
Sir, for future.
Yeah, we will see when we come this month. It will be only input equal to output. I am afraid. Sorry. But then we do energy balance, and then maybe combine mass and energy balance. There will be something more interesting. But अभी तो हम कहाँ पहुँचे? ठीक है, we will see when we'll cross the bridge when we reach it. Okay.
Mm-hmm.
Yeah.
Thank you, sir.
Yeah, welcome.